Welcome to video lecture B7. This one is on coordinate systems. I'll be your trainer, Tom Roby, and here are the outline and objectives. We'd like to demonstrate that every vector has a unique representation in terms of a basis B for a vector space V. I think I've mentioned this before, but we know that we can always write things in terms of a basis because it's a spanning set. But we haven't shown that this representation is unique. And we'll need that in order to define coordinates for any given vectors relative to a given basis. So in some cases where we already have a standard basis, then we can view the sort of matrix we get as a change of coordinate matrix. We'll call it P subscript B. So we've got this basis script B, and we'll have a change of coordinate matrix that'll let us change the way we view things from one basis to another. You can think of this in a way as being, it's not exactly perfect analogy, but it's sort of like moving from between polar coordinates and rectangular coordinates. You know, you've got the standard one that's rectangular, and we'll be looking at coordinate systems which are not circular so much, but that, for example, look like instead of a rectilinear grid, you've got some grid that is like, looks like you've tiled it with parallelograms. That's the kind of thing that you can get. So here's the unique representation theorem. Suppose I've got a basis, vectors b1 through bn, then every x in the vector space has a unique set of scalars c sub I, so that x equals c1 b1 plus dot dot dot, that should be a plus cn bn. I guess I can add the plus, right? Okay. So why should this be true? Well, we certainly know we can find Ci satisfying 1 because B spans V, right? So just that's the definition of span, right? But why should it be unique? Well, let's suppose that we had a representation of x as d1 b1 plus dot 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 plus dn bn as well. So we've got these two different representations, and so now I claim that the Ci's and the di's have to be equal. So why is that? Well, if I know that x equals both of them, then what am I really saying? I'm saying that c1 times b1 plus dot 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 plus cn times bn is equal to d1 times b1 plus dot 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 plus dn times bn. Okay? So now if that's true, I can subtract. I can write each of these, I can subtract all of these, move them to the other side, and I end up with c1 minus d1 times the vector, this vector basis, b1, plus and so on, plus cn minus dn times bn, that's just equal to 0. Aha, but what do I know about a basis? A basis is a spanning set that's also linearly independent. So if it's linearly independent, then if I have any linear combination of these vectors that's supposed to give me 0, then that means each of these coefficients has to be 0. So this implies that c1 minus d1, c2 minus d2, and cn minus dn are all equal to 0. I guess I should say equals 0. Equals 0 since script B is linearly independent. Okay. So that's all there is to that uniqueness proof. And so what that lets us define is coordinates, right? So I'll say that these weights are the script B coordinates of x. And I'll just write them like this. I'll write, you know, the coordinates of x with respect to B are c1 through cn. And usually what I'll do, it's a little confusing because Lay doesn't do this as consistently as I would like, but I would usually write this c1 through cn, and then I'd put a little script B subscript next to it so that I'm clear on what my units are. Okay. So this is sometimes also called the coordinates of x with respect to the relative, the coordinates of x relative to the basis B. That's a longer-winded name for it. All right, so suppose I've got this other basis. Script B is 1, 2, 2, 3. And maybe before we even do anything very computational with it, let's just think about what that would look like. Well, so that means that I'm in my usual space, let's say this is r squared now, right? So I'm in r squared. So I've got my 0. And now I'm saying, I'm looking at linear combinations of 1, 2. Okay, so that means I go over 1, up 2. So I'm here. So that's this vector. And then the other vector is 2, 3. So I'll write that in a different color. So I'm going over 2 and up 3. So that takes me to about here. Okay? And so now, like, I might as well draw the parallelogram that's kind of associated with this. Right? And the idea is that now I'm going to, if I just keep extending these, I can get, the fact that this is a basis means that I can write anything in terms of these coordinates, right? So that means that I'm writing it in terms of these parallel blue things and the parallel red things. Okay? So instead of tiling things rectilinearly, what I end up with is this. Maybe it would look better if I didn't make them dashed. Maybe if I just like drew them this way solidly, you could see them better. And then these guys. And I'd need to draw more of them to make a really good picture, but right. And so you see you've got all these kinds of parallelograms that are tiling the plane, and that's how you're understanding where something is. Any point in here can be represented as, well, how far along am I along a blue, and then how far am I along the red? Okay, so I don't know if that was clearer or helpful, but you don't really need to understand it that way unless that's helpful, but you might look at the pictures in the book. But let's take a quick look at this example. So if b equals 1, 2, 2, 3, and I want to say, well, what is 4, 1? Well, 4, 1 in b coordinates means 4 times the first vector minus 1 times the second vector. Okay, so 4 minus 1 b means 4 times 1, 2 minus 1 times 2, 3. And let's see, what's that? That's 4 minus 2, which is 2, and 8 minus 3, which is 5. Okay? And so this is, when I write this to 5, I mean for this to be in the standard basis, and sometimes I'll just write that as script E. So script E, by definition, in this context, I mean script E is going to be the standard basis, which is 1, 0, 0, 1. In general, it's all the columns of the n by n identity matrix in R to the n. So that's, with that respect to that standard basis, you're thinking about everything as being gridded the usual way, right, by little squares instead of by parallelograms. All right, so 2, 5, so going out 2 and up 5 in the usual way is going to be the same thing as going out 4, or I guess 4 along the red and then minus 1 along the blue. So that's the idea here. Okay. So here's what we've got. We've got, of course, this linear combination, 4, negative 1b equals 4 times this. I can really think about this as just being, right, this by definition is take the matrix of this basis, 1, 2, 2, 3, and multiply it by 4 minus 1, right? Because that's what taking this linear combination of the vectors means. So I can really view my conversion from b coordinates to standard coordinates as being multiplication by the PB matrix. Okay, and so that's the definition of this change of coordinate matrix. All I need to do to make this matrix, it's really easy. All I do is take the basis elements and put them into a matrix. So I take 1, 2, 2, 3, I put them into the matrix. This is the matrix PB. And so then the property I'll have is that if I want to know what x is in standard coordinates, then all I have to do is multiply PB times something that's in non-standard coordinates. And really what I'm saying here, Really, I'm saying that x in standard coordinates, even though the book just writes x. When it just writes x like that, it means that I'm thinking about it in standard coordinates. Okay? So now suppose I wanted to express something like 0, -1 in terms of b. And I'm going to run out of space here, so I think I'm going to take a break to erase, and then we'll come back to this. Okay, so let's look at an example of this. Suppose that I know that 0 -1 is the standard coordinates, and I want to express it in terms of these funny coordinates, 1, 2, 2, 3. How would I do something like that? Well, so I need to solve the equation. I know that 0, -1 in E is equal to PB times something, x1, x2, in B coordinates, right? So what am I saying? Well, in this particular case, that means I'm trying to solve 1, 2, 2, 3 times x1, x2 has to be equal to 0, -1. All right, so now I'm just back to a row reduction thing. So I could do the row reduced echelon matrix if I wanted. So I could, you know, you can solve that, or, right? And if you do that, so this implies, I don't want to do this. This is too easy to do another example of here. But this implies that x1, x2 should be equal to, I think, -2, 1. And how can we check that? Well, let's check what happens when we make the -2, 1 linear combination of this. So I'll get -2 plus 2 is 0, and I'll get -4 plus 3 is -1. So that must be right. Okay, but I just did this by making the augmented matrix 1, 2, 2, 3, and then 0, -1, and row reducing. But what I really want to emphasize is another way you could do it, which is, you know, sometimes when you're changing coordinates, you have a lot of different vectors that you want to change the coordinates of. And under those terms, you're just trying to figure out, you know, what 0, -1 is, then you might as well just do row reduction to solve the equation. But in some situations, you might want to actually find the inverse of this matrix, because this equation that I've written down, if I multiply things over to the other side, I can say that, let's see, I think I have this on the slide, that the fact that x in standard coordinates is equal to this change of basis matrix times x in B coordinates. If I move this over to the other side, it's the same thing as saying that xb is equal to PB inverse times x in standard coordinates. So if I know 0, -1 in standard coordinates, I just multiply by PB inverse to get x1, x2. So the question is, what is the inverse here in this case? So recall that if I want to know the inverse of a 2 by 2 matrix, what is that? Well, I have to divide by the determinant, and then I have to do what? Do you remember what it is? You have to negate something and swap some things around, right? Well, so if you don't remember, you can always try it one way or the other and get, but you switch the diagonal entries and you negate, but leave in the same location, the off-diagonal entries. And you can just check, right, that if you multiply it AB times D minus C, you'll get AD minus BC, which is this. You divide by this and you get 1 up there, and so on. Okay, so that's the inverse of that. So that means that in this particular case, that the inverse of 1, 2, 2, 3 is 1 over, okay, 1 times 3 minus 2 times 2 is going to be -1. And then what do I have to do? I have to flop. Okay, so I switch 3 and 1, and I negate -2 and -2. But this guy is -1, right? So I'll just be multiplying everything through by -1. And so I'll get -3, 2, 2, -1 is the inverse of this matrix. Okay? So now so now what? Well, so now I can just say that, well, so for example, if I wanted to figure out, so x1, x2 in B coordinates should be -3, 2, 2, -1 times, well, for example, if I do 0 minus 1, then I just get negative 2, 1, which is the same answer I got before. Okay? So that's handy to be able to go back and forth by using the matrix or its inverse. And now suppose I want to do another one. Well, if I want to do another one, you know, all I have to do is replace 0 minus 1 with 3, 5, right? So x1, x2, b for the answering this question is just equal to negative 3, 2, 2, negative 1 times 3, 5. And let's see if I can do that. Well, it looks like I'll get negative 9 plus 10 is 1, and I'll get 6 minus 5 is 1. So this should be 1, 1 in standard coordinates. Okay? So, and I think that's it for video lecture B7. Thank you very much for your kind attention.